Hello and welcome to our lesson today. This is the second topic in Form 2 we are handling. It's called Indices and Logarithms. And today we are specifically going to handle in the indices part, all right? So that in our next lesson we handle logarithms, okay? Indices is simply talking about the writing numbers in power form. You see, if you raise a number to a certain power, the number that is raised is called the index, and the plural is indices. For example, take for instance 16, right? 16 is a number that can be written as 2 times 2 times 2 times 2, right? It can also be written as 4 to the power of 2, right? Or 2 to the power of 1, 2, 3, 4. Okay, if you look for 4 power 2, you get it 16. If you look for 2 power 4, you get it also 16. Okay, 4 has just combined this pair. 4 has combined this pair. Sorry, 4 has combined this pair and this pair so that you have 2. 2 times 2, this one is 4, that one is 4, so 4 to power 2, and then 2 is just 2, 2, 2, 2, so 2 to multiplied 4 times. It's the same way of writing 16, alright? So this and this are what we call indices, okay? Those are what we call indices, alright? So let's just go very fast to the laws of indices. And I'm going to go to the first law, and the first law is the law for multiplication. Okay, the law for multiplication, now let me just change the color of this pen. The law for multiplication states that if you're multiplying indices of the same base, you just need to add the powers, all right? Now look at this very carefully. You can see I'm having a as the base here, and here I'm also having a as the base, and I'm multiplying them. Okay, the powers do not have to look the same. The moment the bases look the same, the solution is normally just the base, and then you add the powers as I've done there. And I think it's going to be a little bit simple if we do it as an example. Let's say if you have 3 to power 3 and you're multiplying that by 3 to power 4, the bases are the same. Okay, the bases are the same, so the solution is going to be 3, and then you just add the powers, that is 3 plus 4, so the answer is 3 to the power of 7. Right? Right? Maybe we can have a different kind of an example. Let's call that example Roman 1. Example Roman 2, let's say you have 4 to power 2 times 4 to power 3. You can see the bases are the same. So you can easily say it is 4 to power 2 plus 3, and therefore 4 to power 5. Okay? Alright. Let's start getting into a more complicated scenario. What if you have, let's say what? Let's say now you simplify. Let's change this question a little bit. Let's say you're told to simplify the following, and the first one is b, let's say x squared times x to the power of 4. So the base is the same, so you just take the base and then you add the powers, 2 plus 4, that is x to the power of 6. Okay, all right. Hope you're going on well. Now, uh, uh, Roman 2, let's say you have b squared. Remember, we're still simplifying. Times x to the power of 2 times b to the power of 11. Now, this example is very deliberate because these and these have the same base. So those two can easily be simplified. Okay, so bring them together. Let's say they are kind of like terms. So b squared times b to power 11 times x to power 2. And then we can deal with this because of the same base, so that we say it is b to power 2 plus 11 times x to power 2. So this one is going to be b to power 13 times x to power 2. And this is the most simplified uh, form of this thing, right? Don't even think for a second that you can begin adding the powers here when the bases are not there, are not the same. Okay, so that is the answer. That is the answer. Let us look at another one, Roman 3. Let us say we have another one here. Roman 3, a to power 5 times c to power 2 times a to power 3 times b to power 3 times a to power 4. So we are collecting the same basis, the same basis, the same basis. A to power 5 times a to power 4 times a to power 3. Then we go to the other bases that are the same. No other bases are the same, so we just have times c to power 2 and then times b to power 3. So this one we can do the necessary. This one will be a to power 5 plus 4 plus 3 and then times c to power 2 and then times b to power 3. So 5 plus 4 plus 3, that is 5 plus 4, 9, and then that is 12. So we'll have a to power 12, c to power 2, and b to power 3. And of course, as we said, because the powers are not the same, there's nothing much you can do about that, right? I want us to go to the second law. I think the law of multiplication is pretty understood, right? You just, if you're multiplying indices and the base is the same, the base, is the base part, okay? You just have the base and the power. Now, if you have m raised to something, then m is the base and n is the power, right? So if the base is the same, what you do, you just add the powers. Let's just look at the second law. The second law, code number 2, is talking about division, and it kind of relates with the first law. Okay, the first law says that when you're multiplying indices, you of the same power, you just add of the same base, you add the powers. For division, if you're dividing indices of the same base, what you need to do is to, let's say this one is z. What you need to do, because the bases are the same and you're dividing, you just need to subtract the powers. It's kind of the opposite of, of multiplication if addition and subtraction is opposites. Okay, so if say you have 3 to power 4 and you're dividing that by 3 to power 1, you'll just say it is 3 and then you subtract the powers 4 minus 1, so that the answer is 3 to power 3. All right, consider that as our first example. If you have, say, a to power 15 divided by a to power 14, all you need to do is to subtract the powers, right? All you need to do is to subtract the powers, okay? Say you have, say, x to power 7 divided by x to power, say, 2b. right? The bases are the same, so you just subtract the powers. X to the power 7 minus 2b. That's the most simplified manner that one can be written, right? I want to assume that the laws of division is understood. Let us look at a little bit more complicated example about the same. That one is going to be the fourth example. 25 y to the power of 9k negative 7 over 81y 7k to 9, right? So this is negative 7. Let's it a little bit. Yes, and then I'm going to go ahead and kind of separate this thing. I'm going to say it is 25 over 81, and then there is y power 9, and then y power 7. And then there is k power negative 7, and then k to power 9, right? Now it's like saying, let's say you have 2 times 9 times what? No, like times 7, right? Over 2 times 3 times, say, 7, right? Is it right if I just say you cancel that, and then you cancel that, and then you cancel that, and the answer is 2, right? Is that correct? Let's confirm it if it's correct. 2 times 9 times 7. So 2 times 9 is 18, and then times 7 is 126. Right, the numerator is 126, and then 2 times 3 is 6, and then times 7 is 42, right? Is that so? 2 times 9, uh, 2 times 9 is, yes, so 140, 126 divided by 42 is 3, right? And when we cancelled here and here, this one divided 9 by 3, actually not 2, so the answer is 3, right? See, I was just trying to show you that we can separate this, right? We can separate this so that we divide the like terms, okay? So for this one is simply going to be 25. Let's scroll a little bit. This one is going to be 25 over 81. This one is going to be y power 9 divided by y power 7. This one is going to be k. Alright, so let me just do that very fast. This one is going to be k power negative 7, and then k divided by k power 9, because it's below there. So that we have 25 over 81 y, and then 9 minus 7, it's division, k negative 7 minus 9, right? So that our final answer will be 25 over 81 y power 9 minus 7, that is going to be 2, and then k power negative 7 minus 9 is going to be negative 16, right? That will be our final answer. Okay, there it is, right? And remember, you can always pause the video and solve this by yourself before you follow up on the solution and you do it. Okay, so let us look at another thing. Let us look at another thing. Alright, kind of combination now. Let's look at combination of the laws we have talked about. Right, we have talked about the law of multiplication and division, so let us look at a combination of the same. So let us have another example. I don't know if it's the number of the example. So it is a power negative a b power 2 times b power negative 4 times c power negative 4 over a power negative 2a times b power negative 2a times c power negative 2a. Right? So we're going to very fast begin with the numerator. Right? Let's begin with the numerator. And I think the a power negative a b power 2 times b power negative 4 times c power negative 4. We're starting with the numerator, and this one can be multiplied, right? Because this base and this base are the same. Okay, so that we have a power negative a b power 2 and then plus negative 4. Right, because it's multiplication, we are adding the powers, remember, and then times c power negative 4. All right, so here we can have a power negative a, and then b power, this one will give us a negative 2 minus 4, that one is negative 2, and then times c power negative 4. All right, and I'm going to just say this is a power negative a times b power negative 2, and then times c power negative 4. Let's look at the denominator. The denominator is a power negative 2a times b power negative 2a times c power negative 2a, and all the bases are different. There's nothing you can do about that, right? So we just combine them so that we finish the simplification. We have a, that is to negative a, times b to negative 2 times c to negative 4 over a to negative 2a times b to negative 2a times c to negative 2a, right? And we're going to repeat the same thing we have just done in our previous example. We're going to divide this, and then divide this, and then divide this, right? Very fast. So a to power negative a divided by a to power negative 2a, and then we have b to power negative 2 divided by b to power negative 2a, and then we have c to power negative 4 divided by c to power negative 2a. Then we're going to just use the law of division, right? So that we say a to power negative a minus negative 2a, and then b to power negative 2 minus negative 2a, right? And then c to power negative 4 minus negative 2a. You've got to be very careful with the signs, right? You have to be very careful with the signs. So that here we are going to have a to the power of negative a plus 2a, b negative 2 plus 2a, right? And then c negative 4 plus 2a. And I don't understand why this is a. Was it a since the beginning? Right. So that's correct. Okay. Uh, I want us to look at something else. I want us to look at the third law. We have just looked at the law of multiplication and the law of division. I want us to look at the third law, the power law. Right. And the power law states that if you have a to the power of m and you're raising it to another power of n, what you need to do is to multiply the powers, right? For example, if you have, say, 7 to power 7, and you're raising that again to power 2, you're going to have to multiply the power so that you have 7 to power 7 times 2, which is 7 to power 14, right? Maybe let us look at another example. Maybe if we have 7 to power 5 and then to power x, we're going to have 7 to power 5 times x, which will be 7 to power 5 x, alright? So we are basically just multiplying the powers, right? When we have two powers, we multiply them. 3 to power 2x, and then again to power 4 is going to be 3 to power 2x times 4, which is 3 to power 8x, right? It's as simple as that. It's as simple as that. Another thing, I'm going to call it a principle that we need to know as far as indices are concerned is about the zero index. The zero index. And I'm going to write a statement here and say anything to power 0 is equal to 1, right? Anything raised to power 0 is equal to 1, like a to power 0 is 1, b to power 0 is 1, right? C 7 to power 0 is 1, right? 8 to power 0 is 1. We are talking about 1000 to power 0 is 1. It doesn't matter what it is, so long as it is raised to power 0, it is 1. You know where it came from? Let's say you have 3 to power 3, right? Over 3 to power 3. Okay? We know 3 to power 3 over 3 to power 3. You know there are two ways you can do this, right? You could just cancel them and the answer is 1, right? Or you could say 3 to power 3 is 27. 3 to power 3 again is 27. 27 divided by 27 is 1, right? Now, if we use indices to solve this, we would have said that 3 to power 3 divided by 3 to power 3 is 3 to power 3, right? Because it is division, we subtract the powers, we get 3 to power 0, right? And we say that this is equal to what? To 1, right? Because 3 to power 3 divided by 3 to power 3 is 3 to power 0. And we know 3 to power 3 divided by 3 to power 3 is what? Is 1. So 3 to power 0 is always equal to 1, right? Another uh, very important principle that I want us to understand is called the negative indices. The negative indices, right? The negative indices. Say we have a to power 0 divided by a to power m, right? That will be, its division, so it will be a to power 0 minus n, which will be equal to a to power negative what? Negative n, okay? All right? Now, a to power negative n, therefore, a to power negative n is the same as a to power 0 divided by a to power n. I don't know if you're seeing what I'm saying. I'm saying a to power 0 divided by a to power n imetupatia, it has given us a to power negative n, right? Now, so that means a to power negative n is the same as a to power 0 divided by a to power negative n, which can also be written in this form, right? And this is a very general form, and a to power 0 is 1, right? So it is like saying it is 1 over a to power n. So a to power negative n is just 1 over a to power n. Basically what we're doing is we are putting this under, and then we are leaving the sign out, the negative sign out, right? So a to power negative n, you just say 1 over the same thing, a to power n. Now you assume the negative. For example, if I have 3 to power negative 3, I'm saying it is 1 over 3 to power 3, which is 1 over 27. If I have 27 to power negative 2, it's just the same as 1 over 27 to power 2, alright? If you have 7 to power negative 3, it's just the same as 1 over 7 to power 3. You put it down and then you forget about the negative, okay? And finally, the final principle that we need to understand, right, is called the fractional indices. Okay, right. And, I'm going to start from the most basic, part. If you have uh, a raised to p over q, in other words, this is an index where the power is a fraction. All right. If you have an index where the power is a fraction, you just put that sign there, and then this one is put inside, and then this one is put there, and then this one is put there. Right? Right, and let's put it in a more realistic, numerical example, so that it becomes a little bit easier. If we are looking for 27, say to the power of a third, I'm saying you just say this one is the root there, right? And then you put 27 there, right? And then 2, 1. You don't have to write it there, okay? So it's the cube root of 27, which is 3, okay? Let us change the color for a change. Let's change the color for a change. Let's say we have 8 to the power of 2 over 3. We're saying that what you're going to do is we're going to have the cube root now, the cube root of 8, and then you're going to raise to the power of the numerator, right? So you put the denominator behind the sign, and then you raise it to the numerator, okay? So the cube root of 8 is 2, 2 cubed, 2 squared, 2 squared, 2 squared. Remember, this one went there, this one went inside, and then this one went there, right? So 2 squared is 4, right? And you can check that in the calculator. If you put 8 to the power of 2 over 3, the answer is going to be 4. I'm sure some people have gotten weird answers. If you just say 8 and you raise it to the power of 2 over 3 without putting 2 over 3 in bracket, you are probably going to get 21 on the third, right? Or 21.33333, which is very wrong. 3 recurrent, right? Which is very wrong, right? Why? Because when you just say 8 to the power of 2 over 3 and you don't put it in bracket. What the calculator is going to do is it's going to say 8 to the power of 2, and then it's going to divide the answer by 3, right? So 8 to the power of 2 is 64, and it is 64 over 3, that is 21 recurrent. So you have to tell the calculator that it's 3 raised to power 2 over 3, so that it gives you the answer as 4. Right, that was a by the way. Let us have another example. Let's say you have 16. You have 16 power 7 over 2. So you're saying you'll get the square root of 16, and then you'll raise that to 7, right? And the answer is going to be 4 to power 7, which is going to be 16,384, right? Just consider another example. To 16 power 2 power third. So to 16 times to 16 is going to give us 46, 656. And then now power third means the cube root, right? Remember, power third means the cube root. Because this is going to be to 16, to 16 squared is going to be 46, 656 power third. And as we said, power third means the cube root of this to the power of 1. We do not have to write the power of 1 because the power of 1 means 1. Okay, so we're going to have fun a little bit here. We're going to find the cube root of this using factor method. So I'm going to twist the screen a little bit. 46, 656. Looks like 2 can go in there. 46, 656 divided by 2 is 23, 328 divided by 2 is 11, 664 divided by 2 is 58, 32 divided by 2 is 59, 16. 29, 16 divided by 2 is 14, 58 divided by 2 is 729. And I believe that is where division by 2 stops. So divided by 3 is 243. Divided by 3 is 81. Divided by 3 is 27. Divided by 3 is 9. And divided by 3 is 3. Right? So when you're finding the cube root, you just take a pair out of every 3. Take a pair out of every 3. So you have 2 times 2 times 3 times 3. And the answer is 36. Right? So the answer right there is 36. And I want us to go to a little bit of application now of the same. We have like how many? Like 5 or 6 examples in application of the same of the concepts that we have learned. And then we call it a lesson. Right? So let's say solve. Now solving is finding the value of something. Let's say number 1. Let us solve 3 to power 2x power 3, it's equal to 3 to power 4, and then times 3 to power 8. Okay, so with this one we are going to just use the power rule. So we are going to say 3 to power 2x times 3, it's equal to 3. I think this side we can use the multiplication rule, so that we say 3 to power 4 plus 8, right? We are adding because of multiplication. So 3 to power 6x is equal to 3 to power 12, right? Now uh, the moment we have 3 to power something is equal to 3 to power something, then it means that the powers must be the same. Alright, so we can drop the powers the moment they look the same, like that. So 6x is equal to 12. Alright, now x is equal to 2. Alright, let us look at another one. Let's look at another example. Let us solve 7 to power 5. Alright, let's solve 7 to power 5 to power x. It's equal to 7 to power 4 to power x divided by 7 to power 2. Alright, so we multiply that. Remember, m power n x is simply m power n times x. So 7 power 5 times x is equal to 7 again power 4 times x divided by 7 power 2. So this one is going to be 7 power 5x is equal to, now this one is division, so it's going to be 7 power 4x minus 2, right? So that we have 7 power 5x being equal to 7 power 4x minus 2. I don't know why I've just written that again, but when we reach here, we can see that the bases are the same. So if the bases are the same, you can just drop them, so that 5x is equal to 4x minus 2. So the powers are the same. Take that one to the other side. 5x minus 4x is negative 2. Therefore, x is negative 2. Right? We can look at another example, third example. Right? So that we solve 3 power 2x minus 5 is equal to 27. Take a moment and just pause the video so that you try and solve it before you see the solution. So this one is 3 to power 2x minus 5. Remember, our target is to ensure that we have common bases on the opposite sides of the equal sign, so that we can drop them. And 27 can be written as 3 to power something, because 3 goes there 9, 3 goes there 3. So 27 is simply 3 to power 3. So we write 27 as 3 to power 3, and that leaves us with the bases that are the same and droppable. So we have 2x minus 5 being equal to 3, and therefore 2x is 3 plus 5, right? So 2x is 8, and therefore x is 4. All right, we can look at the fourth example. The fourth example is 9 to power 4x, and then divided by 3 to power 2x is equal to 2187. Again, pause the video, try solving it, and see if you get the answer. Of course, we can write this as a base 3, and we can try to write this as a base 3 also. Check if so let's use factor method real fast. Alright, we're going to check if 3 goes there, if 3 can divide 2187. So let's see, 2187 divided by 3, it divides 2187 729 times, again divide to 729, 243 times, again 81 times, again 27 times, again 9 times, and 3 times, right? So it is 1 2 3 4 5 6 7, right? So this one is 7 to power 2, 9 is 7 to power 2, and 9 is raised to power 4x, divided by 3 to power 2x, and this one is 3 to power 7, as we have seen here, right? So this one is multiplication, so 3 to power 2 times 4x. I'm going to skip that step, you know what to do. So we are just multiplying the powers, 2 times 4x, that is 8x, then divided by 3 to power 2x is 3 to power 7. Then we are pulling the law of division, so 3 to power 8x minus 2x is equal to 3 to power 7. So 8 minus 2x, now we can drop the bases because they are the same. So 8 minus 2 is 6x is equal to 7, and therefore x in this case is 7 over 6. I hope your solution is the same as that one, because that will mean you understood. Let us go to the fifth example. Right, so 2 to power x over 4 is equal to 8. Alright, again, pause the video, solve it, and then check later to see if you got the answer correct. Alright, now 8 is simply 2 to power 3, right? You know, 2 goes there 4, 2 goes there 2, right? So 2 times, 2 times 2. So this one is 2 to power x over 4 is equal to 2 to power 3. Okay, so the bases can be dropped because they are the same. So that's x over 4 is equal to 3 over 1. So cross multiplication. Therefore, x in this case is 12. Alright, x in that case is 12. I think we can have one more last example. Right, and it's number what? I think it's number 7. Oh, number 6. Alright, let's have a last example. A to power negative n, let's use red. A to power negative n times m times a to power negative 2m over a to power mn times a times a to power 2m. And of course, the first thing is, let's handle the numerator first. So in the numerator, we can start by that. So we have a to power negative nm times a to power negative 2m. The bases are the same, we're multiplying, so it is a to power negative nm, and then plus negative 2m, which is going to turn to a negative nm, plus and minus negative 2m, right? You can look at the denominator. In the denominator we have a to power nm times a to power 2m. Again, now we add a to power nm. The nm and the mn is the same thing, it's multiplication, and then plus 2m, right? Now we can combine them. Numerator and denominator. The numerator is a to power negative nm minus 2m over a to power mm plus 2m, and I'm going to say it is just a to power negative nm minus 2m, and then divided by whatever is down there, a to power nm plus 2m, which leaves us with the subtraction now because of the division on the same base, right? So we have a to power negative nm minus 2m, and then minus this, which is nm plus 2m. It's very important to put them in a bracket because this negative affects everything inside there, right? So we have a power negative nm minus 2m minus nm, and then minus 2m. You can collect the like terms. A is negative nm minus nm minus 2m minus 2m, so that we have a final answer as a power negative 2nm, and then minus 4m, right? And again, I hope you are able to get that answer because it means you actually understood what we did, right? I hope the lesson was helpful and you understood. If you have a question, you can leave it in the comment section. It will be responded. You're advised to go to the textbook and look for more exercises where you can do practice. And if you have a problem with any question, you are also allowed to post it in the comment section so that we can work on it, right? Have a nice time. It was your teacher Patrick.